Can you see my screen?
Yes.
Yes.
Okay. Yeah. So it's just one example of one famous architecture, in fact, which is used heavily in many applications. It's called AlexNet. I will talk about AlexNet next time in more details, but this is just one example. And it's a model which has around 60 million examples. And if you can see here, this is the input volume. This is the input, which is RGB image, right? So if I will go back to it here, this one, it's RGB image, and the size is 227 times 227 times 3. And how many layers we have here? It's AlexNet. How many layers? 1, 2, 3, 4, 5, 6, 7, maybe 8. Yeah. So at the end here, we have 3 fully connected layers. Do you see here? We have here 3 fully connected layers. And it is used for classifying 1,000 classes. So at the end here, we have softmax layer, which is used for, calculating probabilities. And for this input volume, we use here filter size 11 times 11, if you can see it here. So this is the filter size 11 times 11 with stride equal 4. So from this input volume, you will get 96 feature maps. Each has a size of 55 pixel times 55 pixels, right? So this is the first convolutional layer. We can say that this is CNN1, for example, CNN1. First conv layer. We have here filter size is 11 times 11. And of course, it's 11 times 11 times 3, right? Because the input image, it's RGB, which is 3 channels. Stride equal 4. So the output volume of the feature maps will be 55 times 55. But how many feature maps? How many filters we need to define here? Here we defined 96 filters, and each filter will generate a feature map. So the output volume here, or the feature map here, it will be 96. Each has a size of 55 times 55, because in fact we defined here 96 feature maps and 96 filters. After that, this is the first CNN layer, for example. It will be followed by max pooling. The max pooling size will be 3 times 3, stride equal 2. So the output will be 27 times 27, and the same number of feature maps. So it will just impact. It will just try to consolidate. We agreed that max pooling or pooling layer, it consolidate those features, those extracted features. So we will have the same number of feature maps, which is 96, but the size of each feature map will be reduced into 27 times 27. After that, we will use 5 times in the second. This is CNN2, right? This CNN2, we will use filter size 5 times 5, right? And we will use zero padding. When we are use zero padding, we expect that the output size will be the same as the input size. So the input size here will be 27 times 27. But the input here, it has depth equal 96. That means the depth here, it's the number of feature maps, which is 96. But here we defined that we need to extract 256 feature maps from those 96 feature maps, right? So in fact, the filter size here will be 5 times 5 times 96, correct? So the filter size here, it's we just defined it 5 times 5. We don't need to define depth, because the depth will come automatically from the input volume. So the input volume to this CNN will be 96. This is the depth, 96. So you can just imagine that the filter size here will be 5 times 5, 5 times 5 times 96. And it will generate 256 feature maps. Each has the same size, because we used here same padding or zero padding. After that, we will apply max pooling. The max pooling will be the same size as the first one, which is 3 times 3 with stride equal 2. So it will generate 256 feature maps. Each has a size of 13 times 13. After that, we will apply, this is CNN2. This one will be CNN3. the filter here will be 3 times 3. We use the zero padding. If you are using zero padding, so we will get the same width and height and width, correct? But the input here, the input volume has 256 depth, right? So the filter here, it will be 3 times 3 times 256, in fact. And we need to generate 384 feature maps. We will apply again no, we didn't apply max pooling. We will just apply again another filter. So this filter will generate the same number. It's just maybe also with zero padding. It will generate the same number of feature maps. We will apply it again. It will generate this number, but this is the number of features which we need to extract. And at the end, we will apply max pooling here. When we apply max pooling here, with the stride equal to, the feature maps will be 6 times 6 times 256, right? After that, we will flatten this one here. We need to have here flatten, right? We need to flatten this one. So the size of this 1D vector, it will be 6 times 6 times 256, which will be, I guess, this number. At the end, we define the 3 fully connected layers. This is fully connected layer 1, fully connected layer 2, fully connected layer 3. And at the end, we have softmax layer. We have here softmax layer. So in fact, we have like 4 fully connected layers. Number of units here will be 9,212. Number of units here will be 4,096. The same also number here, number of units. Number of units here, in fact, in the softmax will be 1,000, right? Because we have 1,000 classes, which we need to classify. Do you want to calculate number of units, number of trainable parameters? Do you want to take an example? Can you select, Ali, for example? Can you select one layer where we can calculate number of trainable parameters?
In fully connected or overall?
Just anyone, just select anyone. CNN2, for example. Yes, how many parameters here?
Yeah.
How many parameters here?
I think it's so 27.
No, not width and height. We don't care about this. The most important for us is the filter size. Yeah, the filter size, which is 5 times 5 times
96.
96, because this is the depth. 96. Okay, how many of those filters? How many? So this is the size of the filter or number of parameters. But how many units of those? This number 256. So this one will be multiplied by 256.
256, yeah.
Plus 256, which is a bias.
So we don't care about the depth of this CNN?
No, the depth. We have the depth here. This is the depth from the first layer. It's the depth of the input volume. So which is 96. So it will be this number. So if I want to multiply this number here, we can just multiply it. So it will be 5 times 5 times 96 times 256 plus 256. Yeah, so it will be 6 million. No. It will be, okay, 614. 614. Yeah. 614. 650. 656. Yeah, it will be like this. So is there anyone else who can help us to calculate number of weights, for example? Yeah.
When we use different channels, like RGB channels, if we just use the grayscale image, what's the difference? What would be different in this, Alex?
I mean, it's information. You have information, in fact, in your image. When you use one channel, you can, do you know grayscale? It's average. You can take average, right?
No,
so if you have an RGB image, you can convert this RGB into grayscale, for example.
Yeah.
You can convert it from RGB into grayscale. and work with the grayscale instead of working with RGB. But it's information, right? Maybe this
No,
information is important.
not about that part. I just want to know the difference in this model, which the parameters change with using, like for example, our image is not in different colors. It's just grayscale image.
Yeah, it's a grayscale. Yeah, so it will be exactly the same, no difference. But when we calculate the number of parameters in CNN1 here, it will be 11 times 11 times 96 plus 96. So we will not have the depth, which is 3. So in this case here, I mean, number of parameters here, what will be the number of parameters here? In this case, it will be 11 times 11 times 3 times the number of feature maps, which is 96 plus 96. It will be this number. If your image is one channel, this number will be 1. This one will be 1. Right? I mean, this is the only difference. I mean, there is no big deal, in fact. But if this model has been trained for RGB, your input must be RGB. So AlexNet has been trained for RGB images, so your input must be RGB, right? Because this AlexNet, because AlexNet in transfer learning, we just transfer the model as it is and apply it to another problem. So in fact, we keep those convolutional layers or feature extraction layers as they are. In fact, we don't touch it. We just try to modify the fully connected layers. Maybe the last 2 layers, for example. Maybe this one and this one. Not more, in fact, right? So we need to have the input which is the same size, the same depth, and so on. But also, as you can see here, the size of the image, it's not a big deal, right? The size of the image here, it's not a big problem because we scan the image, right? So when we use those transfer learning models, they will tell you what will be the size of the input, what is the accepted size of input image, right? Because the size also is important for those numbers later on. So it'll tell you what is the accepted size, in fact, of input. But the size is not a big deal. I mean, but the most important is maybe the depth is very, very important. It should be the same depth. Yes, in transfer learning, for example, in this AlexNet has been used for classifying 1,000 classes. If I want to use this one for MNIST dataset, for example, so I just need to change those 1,000 classes into 10, right? So just modify it and retrain the model, right? Retrain the model using MNIST dataset and just apply it for and deploy it, right? So, but in this case, we need to look weights of convolutional. We don't need to retrain the convolutional part. We need to use the convolutional part as it is, because all images have something common, in fact, between images. So if I have a model which is working with images, so the convolutional part, it should be the same almost, right? There should not be big deal, in fact, to change the weights of the convolutional layers. We need to freeze the weights of the convolutional layers and to adjust only the weights of some of the fully connected layers. So the first part here, we will keep it as it is, that part, but we will try to change maybe the structure of the fully connected layers and try to modify it to my problem. For example, the last softmax layer, if it has 1,000 classes here, and if I want to apply the same model for MNIST dataset, in this case, I need to modify it into 10. So just small changes. And of course, when you change it into 10, you will not use the same weights here. So you need to initialize those weights by random values and retrain that part. I will retrain the whole model to try to find good combinations of weights at the end to solve the problem with better accuracy. So in transfer learning, we will use the model as it is, but we will make some minor changes to the fully connected layers part at the end, which is in charge of the classification part. I mean, you can just say the feature extraction part will remain as it is, but we will change the layers which are in charge of classification part. Yes. There are some best practices, in fact, when we are using CNN. For example, the receptive field dimension. I mean, the default is 2D, in fact, for images. but it could be 1D. If we are working with words, in fact, if we are working with words in a sentence, or if we are working with time series, for example, we can use 1D. It could be also 3D for video, or because video it's RGB. I mean, each frame is RGB image, right? So it could be, and if we have the time also, I mean, it could be, because sometimes in the video we can have, we can convert, for example, each minute. I described it last time in one example, but we can convert it into some input volume. So, for example, the depth will be maybe I mean how many frames per second, and we can use 3D. We can use 3D filter size. The batch should be as small as possible, but large enough to see features in the input data. It's common to use 3 times 3 for small images, and 5 times 5 or 7 times 7 or more for large images. Stride width, use
I'm sorry, I don't have your voice.
Yeah, your audio is lost.
Same with me.
He doesn't.
I think we lost audios now.
He can't hear us.
Okay.
to 0 and call the 0 padding when reading an input data. This is useful when you cannot or don't want to standardize input images size, or when you want to use receptive field and stride sizes that do not, I mean, neatly divide up the input image size. I mean, pooling is a destructive or generalization process to reduce overfitting. I mean, we agreed that pooling is used for, in fact, for try to.
I'm sorry. Can you repeat the last slide?
I mean, for generalization, in fact.
Do you have your
size is almost set to 2 times 2.
I think he doesn't hear us.
Yeah,
in this case, we will
doesn't
record 75% of the activations from the output of the previous layer. I mean, we will reduce the size of the feature maps by 75%, and of course we will reduce number of activation. Yeah, you cannot hear me. Okay.
Can you hear us? We don't.
You cannot hear me now? Sorry. Yes, I cannot hear you, in fact, but can you say something, Ali? You are muted.
Can you?
No, I cannot hear you.
Oh, you can hear me now. Okay. So can you start over from the slide 27? I think 28. At the start of this slide, we couldn't hear you.
He is not hearing you again.
Yes, I can hear you.
Okay.
Okay. Can you start over from this slide 28?
From the last one? 28. Okay.
Which this one, because we couldn't hear you from this.
Okay, but this one is fine.
I didn't have a sound.
No, I think this one, because 27.
Okay, from 27, yes. It's just some best practices in CNN. So we use 2D filter size for images. We can use 1D when we are working with time series, or when we are working with words, for example, in a sentence. I will have an example maybe after 1 week or 2 weeks. We use 3D for video, for example. I mean, in video, it's some frames, and it's maybe if it is number of frames per second, we can try to put it in the input volume and somehow, and we need to specify 3D filter size. The receptive field, it could be 3 times 3 for small images, and 5 times 5 or 7 times 7 or higher for larger images. I mean, in this example, he used here 11 times 11 because the input volume it's 227 times 227. So you can just increase the filter size for input for large images. The stride width, for example, it's 1 by default, which is easy to understand, but you can increase it to 2 for large images, for example. And when we increase the stride to 2, we will reduce number of calculations or number of activations. So we can speed up the calculations and learning process. Number of filters, usually we start with small number of filters at the input layer and increase the number of filters at deeper layer. So if we can go back here at the input layer here, we have 96 filter. But when we go deep, I mean, he selected here 256. He selected here 384. So usually in the input layer, we select a small number of filters, and in deeper layers, we select a larger number of filters. I mean, padding set to 0 and called 0 padding when reading non-input data. This is useful when you cannot or don't want to standardize input image size, or when you want to use receptive field and the stride size that don't match. So the max pooling, I mean, usually it is 2 times 2 with a stride equal 2. And in this case, in fact, we will reduce the size of the feature map by 75%. And when we reduce it by 75%, in fact, we will get rid of 75 activations. Number of activations will be reduced also by 75%. So we will speed up the process. And you know that pooling it consolidate features and try to generalize and stuff like this. Data preparation, consider standardizing input data, both the dimension of the image and the pixel values. I mean, pixel values if you want to standardize it. But I mean, if you are using RELU, for example, I mean, we don't need to do this. 2 or some number of convolutional layers followed. I mean, usually they have 1 or 2 convolutional layers followed by pooling layer. This structure can then be repeated 1 or more times, in fact. So usually you have 1 convolutional layer followed by pooling, or 2 convolutional layers followed by pooling, and you can repeat this block several times in your model. Fully connected layers are often used as the output and may be stacked 1, 2 or more deep. In fact, you can have maybe 2, 3 fully connected layers at the end. And at the end, if it is classification problems, you can have this soft max layer, for example. Dropout, CNN have habit of overfitting. I mean, it can overfit easily, in fact, even with pooling layers. Dropout should be used such between fully connected layers and perhaps after pooling layers. So you can have this dropout. Now we need to work with an example. You have the code here. I mean, if you can, yes, you have the code here, in fact. So you have this CFAR10. You can go to this example and try to open it. And I can share it with you, so you can try to play with this one. So I will share with you. So please just open it and try to make some changes. Try to define a temporary model and try to plot intermediate values. I will share it in the chat here. So yes, so I will go back to this CFAR10. I mean, just some example. I mean, CFAR10, it's a data set which consists of 60,000 images, and each image, in fact, has a size of 32 times 32 pixels. And those images construct 10 classes, in fact. I mean, they are making 10 classes. And the total number, it's 60,000. So we have 6,000 images per each class. And those 60,000 are divided into 50,000 for training and 10,000 for testing. So we have 50,000 images for training, 10,000 for testing, and we have 10 classes. It's like images for airplanes, cars, birds, cats, deers, dogs, frogs, horses, ships, trucks, and so on. And the data set is divided into 5 training batches and the 1 test batch. So each batch, in fact, consists of 10,000 images. So it's already divided into batches. The test batch contains exactly 1,000 randomly selected images from each class. So we have 10 classes. We have 10,000 images for testing. So those 10,000 images, we have 1,000 image in each class. And the training batches contain the remaining images in random order. So it's already, so how can we get it? But I mean, we have it in Keras, in fact. So you can import it from Keras.datasets. So if you want to start working, you can just open maybe a file in Colab, for example, and try to build the model. I mean, maybe you don't need to go to the example which I shared with you, but also it's not working. I don't know why. Okay, now it works. Yes. So you can import the CFAR10 from Keras.datasets. You don't need to download it. You don't need to upload it. You can just import it from Keras.datasets, CFAR10. We have also something called the CFAR100, and it's similar to CFAR10, but this time it has 100 classes. It has 100 classes. So instead of 10 classes, we have 100 classes containing 600 images in each class. I mean, the other one, we have 10,000 in each class, but this one has 600 images in each class. And there are 500 training images and 100 testing, and from each 600, in fact, for each 600, there are 500 for training, 100 for testing per class. So we have the super classes, we have classes, and we have some super classes. You can import it as well from Keras.datasets. You can import C100 directly from Keras.datasets. We have also another dataset which called the color facial recognition technology database. So it's 8.5 gigabytes of faces for training facial recognition software. And it consists of 14,126 images for 1,199 different persons. And I guess each person has 365 images in different times of the day, maybe at different light conditions and so on. So if you can multiply it, I just need to check numbers. So if we have times 365, yeah, no, okay, along with 365 duplicate sets of images that were taken on a different day. I have no idea. Yes. So you have, anyway, we have CFAR10, we have CFAR100, we have this color facial recognition database. We can use it for building models. So we can start, for example, by Keras, by CFAR10, for example. So you can import CFAR10 and you can download it. When you download it, you will get the training set and testing set already ready for your model. You can just try to plot it. Here, in fact, each pixel value has a value between 0 and 255. If you can divide each pixel value, in fact, by 255, you normalize it. So if you want to normalize it, you can just divide each pixel value by 255. I mean, this is a range, because the minimum value is 0, maximum value is 255. So in fact, the range is 255. So when you divide each pixel value by 255, we normalize it. So each pixel values now will be a value between 0 and 1. In the output, we have 10 categories. So you can just, if you want to convert it into one hot encoding, you can use this command to categorical. And this command, we can get it from sklearn to categorical. We can get it from sklearn. So I want to share the code with you, but maybe, okay. So here, in fact, I try to develop very simple CNN model for CFAR10. And as I told you, we can use sequential API for building our model in Keras. And you can just decide how many convolutional layers, how many dense layers, fully connected layers, and so on. But this is very quick structure. I mean, we use the sequential API for building our model here. This is the first convolutional layer. And we try to extract 32. We will use 32 filters. I mean, this number, it's a number of filters. We will use 32 filters, and each filter will be 3 times 3. Each filter will be 3 times 3. We didn't specify here stride. So by default, it will be 1. If you didn't select it, it will be 1. And we will use padding here. So padding equals same, which means we will use padding. It's convolutional layer, and after it, I use the dropout. We should not use dropout here, in fact. But if you used it, it's fine. I mean, but it should be convolutional followed by BB back max pooling, and after that we can use between maybe this max pooling and then maybe the fully connected layer we can use dropout. Anyway, it will work. I mean, so the first convolutional layer, it has we used RELU as an activation function, and the input shape will be 32 times 32 times 3. So in fact, it's RGB image. The input is RGB image. RGB image. So can you calculate number of parameters of the first convolutional layer? How many parameters we have in the first convolutional layer? Can you calculate it? How many weights we need to adjust in the first convolutional layer? Maria, Matea, anyone can answer this, please? Arif, Birhan, anyone can answer this question? How many weights here?
32.
Yeah. So we can start with the filter size, which is 3 times 3, right? So it will be 3.
Am I right? 32 multiplied by 3 plus 32.
3 times 3 times number of filters. How many filters here? No, first is the depth of the input image will be 3. Multiplied by the number of filters, which is 32 plus 32. It will be like,
yeah, 32.
Right? So the second convolutional layer, it will be the same. I'm just using the same. So we try to extract 32 features as well, but you can make.
Can I ask you a question about this count? They have some kind of dilated filters. Am I right? Dilated.
What do you mean?
I don't know, some kind of like an optional argument in COM2, and is in the newest paper they said that it's make it the receptive field a little bit wider, so not get too deep. I don't know. I just
ask you. If you want to increase the receptive field, you need to increase the filter size.
Yeah, select the filter size. So instead of increasing the filter size, they use some kind of dilated filters. It's 3-dimensional, 4-dimensional filters, but with the same size. So I'm just gonna send it to the chat box.
Okay. This is a second convolutional layer, and after that we will use max pooling. After max pooling, we need to flatten. So this is very important to add this flatten layer. So it will flatten, and after that we can define some fully connected layer. We have this one. We can say that it's fully connected layer number 1. This one, it's soft max layer. We can call it soft max layer, for example. And number of units here will be a number of classes, right? And we use the soft max activation function here because we need to get probabilities. After that, we will compile the model. We need to define loss function. We need to define the optimizer, and we just, this model summary. Here we use the plot model. It will plot the model like this graph, for example. And after that, we will train the model. So after compiling the model, we need to train the model. So we train the model. We can get accuracy, which I don't know why this number it's 1.09. So maybe we need to run the model and try to see. Yes. As I told you also, if you want to plot some intermediate values, so in this case, we need to use model API. Last time we used here sequential API. So when you define your model, we use the sequential API because it's a sequence or a stack of layers. So this is my model from, as you call it, end to end. From input to output. So we use the sequential, and in the middle we have all our layers, a stack of layers. So we use the sequential API. But if you want to plot some intermediate values, we need to use model API. Here I use the model API. The input will be the model input, and from where we want to get the output, maybe from layer number 2, for example, from layer number 2. So layer number 2, what is layer number 2? Layer number 2, in fact, it's 0, 1, 2. So it will be this one. It will be layer number. This one it's a 0. Maybe this one it's 1, right? This one it's maybe it's after max pooling. It could be after max pooling. Yeah, maybe. Right? So it will be this one. So if you want to get the output from any specific layer, you need to define a model using model API. You need to define the input. So the input, it will be just a model.input. This is, and from where we need to get the output. So the output, if you want to get from layer 0, layer 1, layer 2, layer 3, and so on. And after that, you can plot it. How can we plot it? We will have base model, new base model, in fact. So this is the base model summary. So the base model, we will have this is the input layer. And first convolutional layer, dropout. So maybe dropout, they consider it as a layer effect. So this one will be 0, this one will be 1, this one will be 2. So we will get the output from this one. So, and of course, we will train the other model, and we will use this one only for getting access to those temporary outputs. So I want to plot the output from the second convolutional layer. So in this case, I defined it as layer number 2, because this one will be layer number 0, first convolutional layer. Maybe the dropout would be layer number 1. And after that, we will have this convolutional layer number 2, right? So those are how many outputs we are expecting from this one, in fact. So if we can go to the definition here, we have 32 feature maps. So we should get, in fact, 32 feature maps from this layer, right? So for this input image, we will have 32 feature maps. It's a 20, 22, so maybe I didn't plot all those outputs. But for each input image, we should get 32 feature maps, right? You need to be sure that you are getting 32 feature maps from conv2, in fact. So from conv2, here, we will get 32 feature maps, and it will be the same size. It will be 32 times 32 times 32. So it will be this size. It will be this one, in fact. So you can just imagine that it's the width and height are 32, 32, and the depth is 32, which is the number of feature maps or number of filters. Yes, it would be nice also if we can plot maybe the filter itself. I have here 32 filters. So if you can plot the values of the 32 filters, it will be very, very useful. So we can understand what kind of filters the model is using. So now here we are plotting the outputs, but also you can plot each filter. So we have, I mean, the filter, it's 3 times 3. So you can try to plot each filter or try to print out the weight values of each filter. Yes, because here in the second layer here, it will be, we will have 32 filters. Each filter has a size of 3 times 3. If you want to do it for MNIST, it's the same also. I used here almost the same model, but I have here the first convolutional layer. The input shape, it's 28 times 28. It's RG, I mean the image, it's a grayscale. In MNIST, in fact, it's a grayscale image, so it's only one channel. So the input shape will be 28 times 28 times 1, right? And the filter size will be the same, 3 times 3. How many filters you want to apply? We need to apply 32 filters. Activation function is ReLU. After this first convolutional layers, we use the max pooling, and it's followed by conv2, max pooling, conv, flatten, right? So we started by 32 feature maps. We increase the number to 64, and this is the best practice, in fact, to start with a small number of filters, and in the deeper layers, you select a larger number of feature maps. So at the end, we will define one fully connected layer, and this is one softmax layer. Number of outputs in the softmax layer will be 10 because we have 10 classes in MNIST dataset. Compile. This one, it's just a standard summary model. You will get those numbers automatically. And this is the number of parameters. Do you want to calculate any number of parameters here? For example, if we need to know how many parameters here in the first layer, in the first conv layer, how many parameters here? How many parameters in the first conv layer? Other people, they are following us, or they are just doing something else?
They are following, but personally, I just get a bit confused with this.
Okay, why?
I don't know.
For me, it's different. It's difficult to see what layer you're referring to. What filter are we dealing with, and how many? What are the dimensions of any input vectors? And then I get lost, and then I'm like, I don't want to make some mistakes. So I'm quite.
Wait, should we check this one here, for example? So do you know in the MNIST dataset, it has those images, and each image, in fact, it's a grayscale, and it has a size of 28 times 28, right? And because it's a grayscale, so it has only one channel. So the input shape here, if we will use this model, the input shape will be 28 times 28 times 1. Because MNIST dataset, it's in grayscale. It's not RGB. In this layer, I need to define filter size. So we will use a filter size which is 3 times 3, just a standard with any, because the image is 28 times 28. You can select 5 times 5, no problem. You can select it 5 times 5. So here we will select 3 times 3. How many filters you want to get, or how many feature maps you want to get from this input image? We need to get 32, so we need to specify this number here.
It's is it 3 multiplied by 3 multiplied by 32 plus 32?
Yeah, this is correct.
Oh.
So is it correct? 320, right? So those 320 parameters, it's a 3.
Can I add something to this?
Times 1, because this is the depth.
Oh yeah, that's fantastic.
Times 32 plus 32. Right? What about the second one? Irini, can you count the number in the second one?
Let's see. It's going to be 3 times 3.
Yes, 3 times 3.
Times 64.
Okay, 64.
And again 64.
Plus
Plus 64, yeah.
But you forget something here.
The times 1, the depth?
No, yes, the depth of the output from the first convolutional layer. The output, I mean, the input here, it's 28 times 28, but the output from this layer, in fact, right, it will be 28 times 28 times 32.
Okay, yeah, I understand. Yeah.
So we have 32 channels. So we need to multiply this number by 32 to be correct. So we multiply this one by 32, we will get this number. Can you try this number, please? So I will try here in my computer. So it will be 3 times 3 times 32 times 64 plus 64. Yeah, so this is 18496. Correct. 18. So it will be correct. It will be the correct number, which is 18496. Yes, the third conv layer, we have this number. Can you calculate this number? Maybe Olga? Can you calculate this number, Olga?
Yes.
Yes. So in the third layer here, in the third convolutional layer, we have this filter 3 times 3. We need to get 64. We need to apply 64 filters, or we need to get 64 feature maps.
So it's 3 by 3 multiplied by 64 and multiplied by previous 64, right?
Correct.
And plus 64.
That's correct. So I will try it here in my computer. So it will be 3 times 3 times 64 times 64 plus 64. So it will be 36928. 36928. So this is correct. This is very correct. Yes. Okay. And after that, we will flatten. And when we flatten, do you see? So this is the output shape. We will get this output shape because we don't use, in fact, do you see? This is the output because we are not using zero padding. So the size of the feature map will shrink. We are starting by 28 times 28. And from the first convolutional layer, it will be 26 times 26. And after max pooling, it will shrink to 13 times 13. In the second convolutional layer, we didn't use zero padding, so it will shrink to 11 times 11. And the max pooling, second max pooling, because we don't use, I mean, after this max pooling, it will be 5 times 5. After third convolutional layer, without max pooling, it will be 3 times 3. So finally, it will be 3 times 3 times 64. This one will be the size of the feature maps. So each feature map, it will be 3 times 3, 9 pixels. So each feature map will be 9 pixels, right? So the size will be 3 times 3 times 64. I mean, this flatten, we adjust those feature maps, we try to put it in a vector, one vector, large vector. Because in fact here, we have 64 images. Each image is 3 times 3. We need to put it in a vector, one vector. So what will be the vector size here in this flatten? So this one will be, we will put it in a vector like this one. So in fact, those one, it's like 64 images like this. 64 one. So it's 1, 2, 3 until 64. And each one, in fact, it's 3 times 3. So we will flatten it. We will put it in a vector, one vector, in order. So starting by pixel 1, 2, 3, 4, up until the end. So the size will be 3 times 3 times 64. I mean, this size, this number. This number, it will be the length of the vector. It will be 1 times 578. So this vector size, it will be one row or one column. It could be one row vector or one column vector. If it is one row vector, it will be 1 times 576. How can we get this 576? It's a 3 times 3 times 64. We can try it. 3 times 3 times 64. So it will be 576. This is correct. So flatten, it does not do anything. In fact, it's just to try to put those feature maps into a vector notation, one vector notation. So what is the number of units in the first dense layer? It's 64, right? So how many weights here? Can you find number of weights here, Olga, one more time? For the first dense layer. How many weights? How can we get this number of weights?
It's the same as previous.
How can we get it?
So it will be the same as the previous one?
No, it's not the same. It's by chance, in fact, by chance, just by chance.
Oh.
But it's not intended, not by intention. So because if I selected here 32, what will be the number? I can change this number. In fact, I can just say, okay, no, this is enough to be 32. So what would be the number here? What would be the number of trainable parameters here? If this one is 32. So if this number is 32, what will happen?
It will be
twice less.
Mm-hmm. So it will be
576 times 32 plus 32.
Yes, so it will be 32 times 576 plus 32.
Yeah.
So do you know, Olga, how can we get this number?
Yeah, 576 multiplied by 32 plus 32.
Plus 32, because this is the number because I mean, when we flatten, we will put those feature maps into one vector notation, and we will connect each pixel value with a fully connected layer. Each pixel value will be connected. It will be the fully connected layer will be like this one. We will have a fully connected layer like this one, which is 32, 1, 2 until 32, and number of inputs here will be the output from the flatten. And the output from this flatten, it will be 1, 2, 3 until 5, 7, 6 pixels, and all those values are connected to. All those values are connected. So number of weights here will be 32 times 576 plus 32 bias values. Okay, maybe Mattia can tell us what will be the number of weights in the output layer. This number 650. How can we get this number?
Right. So that should be the output of the previous layer. That would be 32, right? Times 10 plus
10.
Yeah, plus 10.
Plus 10, right?
This is, I mean, it's originally 64.
Oh, 64, right? Yeah, that's why I was confused, right? So yeah, 32 times 10 plus 10. Okay.
Yeah, so it would be 10 times 64, 640 plus 10.
Yeah.
Yes. So in fact here you can see the advantage of using max pooling. If you didn't use max pooling, maybe the size here would be huge. It would be a very big number, because in the flatten here we have here 576 pixel values. Do you see this number? 576. If we didn't use max pooling, in fact, this number will be very, very large number. And the fully connected layer here, we will have here a huge number of weights. And if the number of weights is too much, chances to overfit will be very, very much higher. So max pooling is very, very important, because in fact it helps us to try to overcome this overfitting problem by reducing number of pixels. You can just say it's reducing number of pixels, because when we use max pooling of 2 times 2 and the stride equal 2, it will reduce the input volume by 75%. And when we reduce it by 75%, we will reduce number of activations, and also the size or the number of pixels will reduce. And when the number of pixels will reduce, the number of weights in the fully connected layer part, it will reduce dramatically. In fact, it will be much, much smaller. So we can say that, okay, our model now, it's okay. It does not have very high capacity, and it should be possible to adjust those to train using the data set which we have. It should be possible to adjust the weights and without going into overfitting. Because if the model capacity is very high, your data set is small, chances to overfit will be very, very high. So using max pooling will help us to have a moderate number of pixel values after flatten. Yes. So you have also the code here. We can go to it later on. But if you want to display some feature maps, it's the same for MNIST dataset. I mean, in this example here, we use the sequential as we did in the last example. We use the sequential API to build the main model, which we used for training. But after that, you can define a sub-model using model API. This one, you can just say it's sub-model. So for example, here in this example, we used CNN1, first convolutional layer 1. I will call it C1. We use the C2, we use the C3, we use the fully connected layer 1, and we use the fully connected layer 2. So this is my model. So if you want to get the output, for example, from here, I need to define a sub-model. The input to this sub-model will be the input to my model. It will be model input. And the output will be the output from the layer which you want to display its feature maps, or the output from this layer. So in this case, you need to use model API. We need to use model API. This is very, very important. Sometimes it's nice to have it in a paper, for example. Sometimes it's nice to display some feature maps, right? Because some people are curious, for example. So, for example, here in this example, for this input image, which is 2, I display here the feature maps from layer number 4. Layer number 4, it's 1, 2, 3, 4. It will be 5 times 5 times 64. Do you see the size? So this one, in fact, it will be, is it 5 or 3? No, it's 3 times 3 times 64, in fact. This is the output from the third convolutional layer, because we have 2 max pooling, right? We have here 2 max pooling. So this is CNN1 max pooling, CNN2 max pooling. This is CN3. So I want to plot the output from this convolutional layer, third convolutional layer. So the size here will be 3 times 3. So the number of feature maps, it will be 64, and the size of each feature map, it will be 3 times 3, and I plot some of it here. So each feature map, this is each feature map, in fact. Do you see? Each feature map, it's 9 values, 9 pixel values. So this one, it's a 3. Each one of those is 3 times 3. And how many of those? It should be 64, which is 8 times 8. So it will be 1, 2, 3, 4, 5, 6, 7, 8, multiplied by 8. 1, 2, 3, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. So it's 64 feature maps. So in fact, this is very nice, because I can display all feature maps from layer number 4. I mean, the order here, in fact, I mean, the index here, we are starting from 0. So it's 0, 1, 2, 3, 4. Right? So this is the output from this layer, which has a size of, which will have a size of 3 times 3 times 64. And this is correct. And this is an example. I mean, if you want to see, I mean, this is one example. I mean, 0 values, 0 pixel value, it's black. And then when it's 1, it's white, in fact, right? So this is also the, I mean, this is the output from this. Those are the numbers, if you want to see. So it's a 0, 0, 0, 0, 0, 0, 0.64, 0.26, 0. So those are the feature maps, which is a model will generate from the input image, which is 2. Yes. At the end, there is something I will talk about it next time also, but it's I want to go to the code, but maybe I can finish this one. Did you hear about 1 times 1 convolutional layer? The filter size, if we selected filter size equal 1 times 1, what will happen? I mean, here in those examples, we selected 3 times 3, 5 times 5, 11 times 11. Is it possible to select a filter size equal 1? 1 times 1.
The asteroid of 1? Asteroid or filter size.
I mean, no, with asteroid equal 1, with asteroid equal 1. So we will use filter size equal 1 times 1 with asteroid equal 1. What will happen?
We'll just reduce the third
Yes.
dimension.
Replicate
Yeah,
the
this
same.
is correct. We just reduce the depth. This is very correct. So for example, so the idea here is to add 1 times 1 convolutional layer before big kernels, such as, I mean, using 3 times 3 and 5 times 5 convolutional layers. And it's they call it reducer, depth reducer, or they call it reducer layer. They call it reducer layer. And this reducer layer, in fact, it reduces the depth of the image, right? Because if you can see here, if this one, it's the input volume, it's 6 times 6 times 32, for example. So in fact, this one, it's each image or each feature map, it's 6 times 6. But how many feature maps from this? We have 32 ones of those. We have 32 ones. It will be like this one. I have. So this is the depth. So we're starting from maybe 1 until 32. So this is the depth. So if you want to reduce the depth, because here I will use 6 times 6, and I need to reduce number of calculations or number of activations. So in this case, I will select 1 times 1 multiplied by the required number of filters. How many filters you want? I mean, I want to reduce this depth into specific number, maybe 16, for example. So if you want to reduce the depth from 6 times 6 into 6 times 6 times 16, for example, you can just use 1 times 1 convolutional layer. And you need to define the new filter number of filters, or the new depths which you want to get. So in this case now, I will convert this volume from 6 times 6 times 32 into 6 times 6 times the required number of filters, right? So the width and height, it will stay the same, but the depth will be reduced. It could be reduced, it could be increased, so it's up to you. But usually they use it for reducing number of depths. So so they call it dimensionality reduction layer. Some people call it dimensionality reduction layer. Some people call it reducer layer. Some people call it bottleneck layer. And it's very important because it reduces number of operations or number of activations a lot, right? Because just imagine how many activations we need here. You need to define a filter here, and the filter size in normal cases, it should be a new filter size times the depth, right? Correct. So it will be huge number of calculations. So for example, I just need, this is an example here. I have this input volume, which is 32 times 32 times 200, and I want to apply this filter size to this one. So how many number of operations we need? How many times operations? It means multiplications, for example. So how many number of operations we need to do in this input volume? So if you will apply this one to this one, what will happen? So we need to get. I will start with the filter size. It will be 5 times 5 times 32 times the input volume, which is 32 times 32 times 200. So it will be this number. In fact, it will be more than 163 million operations. Correct? So it will be really very complex. We need very good computational resources to make those operations. But you can use this reducer layer to reduce the depth from 200 into 32. And when you do this, in fact, you can reduce number of computation into 16.3 million. So in fact, we are reducing it by 90% when we are doing this bottleneck layer, adding this bottleneck layer or reducer layer. How this one will work? You need to define here number of filters, the new depth which you want to get, for example. Applying this one into apply this filter. The filter will be 1 times 1 times 16, because I need to reduce the depth from 200 into 16. So in this case, I will add this reducer layer, and I will define the filter by 1 times 1, just 1 times 1, yes, times 16, in fact, 1 times 1 times 16. Convolve this one with the input volume, it will generate this volume. So the output volume will be 32 times 32 times 16, in fact. Right? And after that, if you want to apply 5 times 5 times 32 into this one, so the output volume will be 32 times 32 times 32 filters. If you can calculate.
Can I ask something?
Yes.
In this calculation, it says 32 times 32 times 16. Is that a mistake?
It's what?
In the
this one.
second,
This one. It is the output volume. This is the volume from this convolutional layer. We will add this convolutional layer, which is 1 times 1 times 16. Right? We will have this convolutional layer here. So the input will be this size, and this is the output size from this convolutional layer.
Yeah, but if I understand correctly, a little bit down, there is this computational cost.
Mm-hmm.
Shouldn't it be 1 times 1 times 16?
Yes, 1 times 1 times 16. Yes, correct.
And then 32 times 32 times 200 instead
yes.
of 30.
Yes,
okay.
multiply it. Just multiply it.
Okay.
So it will be 3.2 million operations.
So this is a mistake in ordering.
Just as the order. Just as the order.
Yeah. Okay.
So it will be 3.2 million operations, right? Which is multiplication. I mean, we count here only number of multiplications, right? But number of activations, what will be the number of activation? Number of activation will be 32 times 32 times 16, correct? This is the number of activation. Can you differentiate between number of activations and number of operations? So number of operations here, he just considered the number of multiplications, but number of activations will be this number, in fact. Correct? And after that, if you want to apply another convolutional filter, for example, so you will get this number here. It will be 32 times 32 times 32. So number of calculations here, it will be 13.1 million. Summing it together, it will be 16.3 million operations. But if you want to apply this one directly, in fact, if I want to apply this convolutional layer or those filters directly to the original input volume, how many number of calculations? It will be 5 times 5 times 32 times 32 times 32 times 200. So it will be 163 million operations. We will get the same volume here, right? But we will get the same volume here, but by 163 calculations or operations. So if you use this bottleneck here in between, you can reduce number of operations by 90% or more than 90%. You will get the same volume. I mean, when I apply this one to this one, we will get the same volume here, right? So it's not a problem. Number of activation will be the same as well, right? But number of calculations will be much more, right? Because it will be 5 times 5. It will number of activations. If we need to get number of activations, it will be 5 times 5 times 200 times 32 plus 32. Correct? No, this is number of weights. Sorry, this is number of weights. Number of activation will be the number of pixels here, because it's pixel. In fact, it's one activation. It comes from one activation. So so the number of activation will be 32 times 32 times 32. Right? Yes, I mean this one. Just it's this reducer. If you want to, maybe you can try it. For example, maybe you can try it in this C400 or I mean, you can try to add it to AlexNet or sorry, for this MNIST dataset, for example, you can try to add one reducer layer and try to see what is there any difference in performance? Is it much faster? You can calculate time, for example. Can we see some improvement in performance? So please try to go to this, for example, this MNIST dataset, and try to add this dimensional reduction layer or reducer layer, for example, and try to see if it has any impact on calculations or the speed. Yes. I want to share with you the code in. I will share this one. But please try to go to Colab and try to make some example. I mean, this is C410, for example. So C410, we will get it from Keras.dataset. I imported sequential from Keras, from models. I use the dense layers, drop out, flatten. From convolutional, we imported conv 2D max pooling. For optimizer, we use the SGD. From Keras.utilities. We have it from utilities, in fact, to categorical. This one, in fact, it will convert this categorical variable into one-hot encoding. Because, I mean, the output here, I mean, Y test here, it's 10 classes. So this one, in fact, it's one column, Y test and Y train. It's one column with 10 values. We need to convert it into one-hot encoding. So we can do this using a two categorical. So I can just run this one here. We can open it in Colab. Yes. Okay. So we have those data sets. Do you see? I mean, this is the output. So I mean, sometimes the output is 6, 9, 4, 1, for example. So this is categorical variable, in fact, because this is the classes. We have 10 classes, so should expect that the number of, I mean, the output here from in Y train and Y test, it should be a number between maybe 1 and 10, for example. We need to convert it into one hot encoding. How can we do this? We can use this by using two categories, using this command. So it will be converted into one hot encoding. So this is the volume of the training data set. This is the size of the training data set. This is the size of the one hot encoding. This is Y train, in fact. This is Y train. So it will be 50,000 times 10 because it has been converted into one hot encoding. So this is X train. This is Y train. This one Y train. X train will be 50,000 times 32 times 32 times 3 because each image, in fact, we have 50,000 images. And each image, it's 32 times 32. And it's RGB image. So number of channels will be 3. This one X train, this one X test. X test, we have 10,000 images. This one, it's for Y test. Y train, sorry. This one, it's Y train. After applying one hot encoding. So it will be 50,000 times 10, right? We will build this simple CNN model using sequential API. You can just change those numbers if you want. So we will do it. So we can have this plot. We can have also summary. We need to fit the model. We need to train the model using X train, Y train. And here I will use X test, Y test for validation. This is not the correct way for doing it, of course. So we will use 20 epochs for training our model. It should be possible to use GPU.
Can I ask one thing in the meantime?
Yes.
In
Yes,
the last slide that you were showing,
yeah.
I got a little bit confused because the dimension of the last filter was 32, and it was applied. The third dimension of the last filter was 32, and it was applied to one which has 16. How does that work?
Which one? This one?
Yeah, it's 5 times 5 times 32, right? And we apply it to kind of make the depth of the volume more. But how do we apply this convolution if we have only 16? Like, do we do some padding?
No. Okay. So I will ask you the same question. I will ask you the same question here. Do you see this one here? Do you see this convolutional layer? The input volume is one channel. It's 28 times 28 only, and we need to get 32 filters. We need to get 32 feature maps. So the filter size here, it's 3 times 3, but we need to extract 32 feature maps from a single image. So we need to get 32 filters and apply those 32 filters to this input volume. And from this each single image, we will get 32 feature maps, right? So we will apply 3 times 3. We will have, how many filters we will have here? We will have 32 filters. Each time when we apply each filter to this input image, we will generate a new feature map. So how many feature maps we will get? We will get 1, 2, 3 until 32 feature maps from a single image. It's the same here, right? We have here as the depth here. Imagine that the depth here it's 16. So the volume here it's 32 times 32, but the depth is 16. We will apply 5 times 5 to each one of those. The filter size will be 5 times 5, but the depth of the filter would be 16 in fact.
Okay.
Correct. And we will apply each filter. How many filters of this type? So the filter size, in fact, in reality, here the filter size would be 5 times 5 times 16. This is the filter size because how many channels here from the input volume? It's 16. So the depth of the filter must be the same as the depth of the input volume. So you can just say that the dimension of the filter will be 5 times 5 times 16. But how many filters? How many feature maps you want to get? How many?
Yeah, okay,
how many
now
different
I understand that.
Yeah. So we need to get 32 filters.
Mm.
Right?
I was thinking that this is 5 times 5 times 32, and then I got confused.
No, it's 5 times 5 times. You just make it like he said that he want to get 32 filters from the size.
Mm. Okay, thanks.
But we don't mention the third dimension because the third dimension we will get it from the input volume automatically.
Mm-hmm.
Right? So it will be the same. So now it's training. Yes, but it takes time for. Yeah, just it takes. We are in the second epoch, so it will take time. But you can just go to the example and try to run the example. Try to modify it. Try to add this reducer layer, for example, and see is there any difference to the same example to this MNIST dataset or CFAR 10. Try to add this reducer layer and try to see is there any difference? Is it more efficient, for example? Yes. So any questions? Any questions for today? I uploaded this slide today to Blackboard and also the slides for next week. Yes. Do you have any questions or do you want to present something? Anyone has any results to present today?
I don't have results, but I still haven't presented the idea for my project. So I would appreciate some feedback on that maybe, but it doesn't have to be today. It's like whenever, maybe you can just look at the presentation or upload it on Blackboard or something. And, yeah.
But you didn't present at all your project?
No.
Okay, we have 10 minutes. We have 13 minutes. So if you can share your, it would be great.
Do you want now or after the results from the?
No, it's fine. Yes.
Oh, okay. Let me try to Yeah.
You are a co-host now, so if you can just
yeah,
you can share your screen.
Can
you share?
Okay. Yeah, you should be able to see it now.
Yes. Yeah, this is clear.
Okay. So I didn't really prepare. Are you seeing the actual presentation or presenter view? Because I have two monitors.
No, this is the actual presentation. This is nice.
Okay. Yeah, I'll try to be quick and efficient. Just it's important for you to get the general idea, and yeah. Okay, so I just started my doctoral studies or PhD studies a couple of months ago around Christmas, and haven't had time to do my domain research. This course actually serves as a kind of a reason to focus on deep learning right away, and that's I try to incorporate that with my main topic of research, which is pertaining to the recommender systems in the field of education. Right, so recommender systems are very widespread. The most common uses, however, are very commercial, either for movies on Netflix or for videos on YouTube or many other use cases. In the field of education, there are some different characteristics that I need to pay attention to, and I try to reflect that with the choice of deep learning paradigm. So I chose recurrent neural networks. And basically my project, the title of my project is implementing or experiences of implementing recurrent neural networks for recommender systems in educational domain. The only way I was able to, after having done some research, to come up with the idea of how to best do this was taking the data from massive open online courses or big platforms that offer some type of challenges or problems for people to solve while learning. This is because the deep learning algorithms by nature intrinsically work well with a large amount of data. With previous applications and previous smaller data sets, this is not really feasible. There have been attempts on older data sets before 2014, for example, to implement deep learning. It just didn't give any satisfactory results. My research questions are as follows. Can RNN-based models achieve satisfying results in the e-learning domain? E-learning is the term that can be used to describe technology-enhanced learning. What are the specific challenges of using RNN for recommending learning objects? Learning objects can be anything from educational videos or text or any type of learning materials that students can consume, or learners rather, not necessarily students. And how should these challenges be addressed? I would like to explore that through this project to make the best possible recommender I can. Looking for data sets presented quite a challenge because finding the convenient or appropriate data set is pretty difficult. Aside from those listed here, there are a couple more data sets that I found in the meantime. I'm still there to do exploratory analysis, but I believe that the one that I will ultimately go with at least in the beginning is the second one here, McKinsey 2018 Hackathon dataset, simply because it is very convenient for so-called collaborative filtering, which is used in recommender systems. I should have mentioned I should have mentioned that a bit earlier. When I said that I will use deep learning or RNN algorithm, that doesn't mean it will be by itself. I will talk about that later. It will be hybrid with some traditional recommender system approaches, most likely collaborative user-based filtering, which is very common for recommender systems. The best ideal data set I expect would be edX data package. edX is, of course, a huge online learning platform, but that package is unavailable to individual researchers. It has to be required by partner institutions, and I don't expect I will have access to it for some time. MooCube is also pretty convenient. It's basically a Chinese version of edX. However, it's mostly in Mandarin, and exploratory analysis, I think, would require too much time for me to do by the end of submission date for this project. KDD Cup is basically a reduced version of MooCube that has been published previously. So this is very tentative timeline. It's definitely not done. I plan to start as soon as possible with development of baseline model and then try to optimize it on the available data. Ideally, later on, I would like to, after I develop an actual model, I would like to expand on additional models or data sets. But we will see what the results, initial results are. This is the general flowchart. So obviously, in my case, this is how the system would work in practice, right? In my case, I don't have access to students in real time because I'm not doing user case study. I work with historical data sets, and obviously I don't control any or have access to any online learning platforms. However, the rest of the flowchart I have planned to implement in this project. So the data sources are twofold. I will have on one side course data and on the other side student data. I feed that to the model. The pipeline is not yet developed, but I expect these steps will be present, right? So from pre-processing to training through hyperparameter optimization and finally evaluation, which is quite a bit, it will require probably a bit more time to complete for the recommender systems because evaluation tends to be pretty tricky. But yeah, when it comes to model, aside from collaborative user-based filtering, which is a staple, I would like to explore with first standard RNNs and then try to implement a bit more advanced model that actually keeps track of the historic user behavior, which RNNs are good for, from what I researched. Yeah, finally, when I obtain the recommendation model, the idea is to actually have for each user a certain amount of recommended content. I plan to do a temporal split, of course, to be able to test and evaluate whether the user has actually consumed the content I recommend to him in future, right? Target conferences are pretty vague at this point because I barely know anything about domain. I just know about the biggest conference there is for recommender system, that is Rexis. The submission date for Rexis is very nearby, so I don't expect I will actually manage to make it for that one, but there are other conferences related to information retrieval or artificial intelligence or education that I can apply and submit to later in the year. As I said, I plan to develop the work further if given opportunity with additional data sets and models and comparison with classical recommender system approaches, which is thoroughly researched, I would say, even on this type of data sets. Yeah, that would be it. I don't know how long I took. Hopefully not too long. Yeah.
No, this is very good. Thank you very much. It's very quick. I shared. I mean, in UVic, there will be a conference. It's UVic. I don't know. It will be in UVic or University of Agder. In fact, it's a conference.
I'll open it right now.
Yeah,
it's
I bought
Agder.
that. But can I answer my phone first? Hello?
Matea, thanks for a nice presentation. Can you shortly explain how RNN are working? Because I
think you
just
will
quickly,
probably
like
do it.
one sentence.
So the main thing is for them to pay more attention or give more emphasis to the previous events. In my case, that is previously consumed content, but it can be anything. So they kind of, compared to, from what I understand, compared to classical feed-forward networks, they not only continue the, the processing to, or give the data to the deeper layers, they also kind of feed the existing layers again. So they kind of retain the same information or the knowledge from previous layers more so than traditional feed-forward networks. They keep track. They're very good for sequential data because when you have to keep track of the sequence, they will be aware of it more so than traditional networks, or I think CNNs as well. Although for my research, CNNs are also pretty used for some of these data sets, but I would just want to explore RNNs, yeah. And then there are also more advanced variants that give special attention, that call tensioned focused RNNs, I think, that will give even more importance to certain parts or in sequence, not just all of recent events, just the ones that you think are most important, but I haven't explored those at all.
Thanks.
Any other questions or comments?
I'm sorry, did you say something?
I'm asking other people if they have any other questions. Any questions? Okay, I shared. You have Maria? You have any questions?
We can barely hear you.
Yeah, it's kind of microphone is.
Maybe.
Yeah, now it's better.
Okay, is it working now?
Yeah.
Sorry for this. Yes, I mean, any other questions? Anyone else has any questions? No? Okay, so I shared in the chat this fourth international conference on intelligent technologies. It will be in 2021 in University of Agder. Last year it was in Gjøvik. It's a nice conference because it's in Norway. So, and it's maybe a good opportunity for people to go to Agder and see it, for example. And I hope if they will be able to, I mean, last year it was digital, in fact. So I hope this time will be physical, so people can go and visit each other. In University of Agder, they have something called the CARE. It's a center of CARE. It's a center of artificial intelligence research. So they are also quite strong in many AI stuff, machine learning stuff. So it will be very, very nice if people can go and attend this conference and present their work. And the conference proceeding will be published in Springer. So I guess it's okay. It's not bad. So just maybe if you write an abstract or a paper, you can just submit it there. If you have enough time to refine it and send it to a more stronger one, you can do it. Otherwise, you can just keep it there, and it will be one publication point, easy publication point. And this conference, it's in Norway. So in fact, we should be able to support this kind of conferences in Norway. It would be nice. Maybe next in 2022, we can have this conference in Trondheim or in Ålesund, for example. I'm thinking to talk to the people to host the version in 2022, maybe in Trondheim, in Gjøvik, or in Ålesund, for example. But it was in Gjøvik last year, in fact. So maybe next time it could be in Trondheim or in Ålesund. It will be very, very nice. So thank you very much.
Yeah. So I just wanted to make sure that the scope is not too trivial, like it is ambitious enough for an actual paper, because I know I'm not pushing the boundaries too much, but for me it's very convenient kind of to learn about both my domain and deep learning.
I mean, it would be nice to have your first publication as a conference, for example, to go present your work, get some feedback. I mean, usually when you attend a conference, you get a feedback which can be used for the future 2 papers or 3 papers, usually. Now we are not traveling, but when I was able to travel, in fact, and attend a conference, usually the feedback which I'm getting from people, it's very, very useful. It can help you to plan for future papers. So just presenting your work there and getting feedback from people, questions, it will be very, very useful for, for our development.
Okay, yeah, thanks.
Different from just publishing in a journal, for example, because when you present your work in a journal, you get some feedback from reviewers. It's not very tough those days because all journals, they want to attract publications, especially those open access. But so it's not very critical feedback, in fact, which we are getting nowadays from journal publications. But when you attend a conference, you get some immediate feedback from people discussing those ideas, how to improve it, for example. So those feedback can be very useful for writing 2 or 3 papers in the next year, for example. Yeah.
Thank you.
Okay. So next week we have this Bosca, this Easter holiday. So I guess we will not have lectures next week, and we will meet the next week after Bosca. Yes. So thank you very much for today, and I uploaded the slides to the Blackboard for this week and for the week after Bosca. And please, if you have any questions, just send it to me directly. Before finishing today, we need to have this reference group for the course. So please try to talk to each other and try to elect 2 or 3 persons to write this midway evaluation of the course or this reference group report about the course. It's something which we were supposed to do it maybe from 2 weeks but please, if you can talk, I can just go out, and if you can talk to each other, elect 1 person, 2, 3 persons to write a report about the course. This report we call it midway report or reference group report from the course. We need one in the middle of the course, and we need one also after exam. And this feedback from you, it's useful for, improving the course in the next years. Yes. So just please decide representative of the course, 2 persons or maybe 3, and just send me their emails, and they should talk to each other. Maybe they can have a chat with each other, talk about, how can we improve the course? What is the feedback? Is there any negative feedback which can be improved, for example? How can we improve it, and so on? Yes, and thank you very much for today, and we will meet again after 2 weeks. Yes. Thank you very much. Have a good day. Thank you. Bye-bye.
Thank you. Bye.
Bye-bye.
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 And Ibrahim, we will have a meeting in the 1st of April. Please don't
yes.
do remember.
Okay.
Yes.
Okay, Ming.
Okay.
Of course. Yeah. Thank you very much.